Okay, good morning, everybody. Let's get started. It's Tuesday morning. As promised, as always, we'll spend a few minutes talking about the assignments to make sure everybody's oriented. Back to the 10,000-foot view for a moment. You spent assignment 1 creating a simulation or virtual world in which your robot is going to exist. And in assignment 2, you spent some time creating some links or some building blocks, the sort of the Lego bricks that'll make up your virtual world and your virtual robot. For the undergrads today, in assignment 3, you're going to start to tackle joints like knee joints and elbow joints that connect links together. And when we get to this particular point in the course, we're going to spend some time talking about pi bullets peccadillos, which is juggling of absolute and relative coordinates. Some of you have got past this point already, so bear with me. Okay, graduate students, last time you focused in assignment 4 on sensors, and you're going to be tackling assignment 5 and 6 this week, which is assignment 5 is motors, and assignment 6 is neurons. So at the end of assignment 5, you finished building the body of your robot, and you'll start in on neurons and then synapses in assignment 7. And today in lecture 4, we're going to talk about artificial neural networks, both inside and outside of robots, which are made up of code versions of synapses and neurons. Looking further ahead, at the end of assignment 7, you will have a full robot inside of a virtual world, and you'll spend assignments 8, 9, and 10 creating an ever stronger evolutionary algorithm that is better and better at evolving robots inside a virtual world to do a better and better job at whatever it is you want robots to do. All good? Okay, that's the 10 assignments in a nutshell. So let's spend a little bit of time diving into assignment 3. As promised in assignment 3, you're going to be attaching links together with joints. And joints and links get a little confusing in pi bullet because it juggles absolute and relative coordinates. So let's start with the simpler case, which are absolute coordinates. They're absolute because they're absolute. I was going to say relative to the world. They're not relative. They're absolute. You just give them a coordinate, that's where they are. So in this cartoon robot here that I'm creating in 2D, I'm just going to rely on Y and Z. I'm placing a link at Y equals 0, X equals 0, and a height of Z equals 0.5. Absolute coordinates should be pretty straightforward at this point. I then add a joint that's going to connect a second link in a moment. That joint has an absolute coordinate. It is at a height of Z equals 1 above the ground. So far, so good. I now add a second link, which is written here in absolute coordinates. The center of this second link, link 1, is 1.5 units above the ground in the Z direction. That is not how pi bullet does things. If it did, it would be so much easier. We would do everything in absolute coordinates, and we would, for example, if we're creating a robot made up of 1, 2, 3, 4, 5, 6, 7 links and 1, 2, 3, 4, 5, 6 joints, be relatively easy to figure out the positions of all of these pieces. Pi bullet does not do that. As you will see in assignment 3, the first link the first link, and in this cartoon, the first joint has absolute coordinates, and afterwards, everything else has relative coordinates. So this particular link here, link 1, which we know in absolute coordinates, has a height of 1.5 above the ground. We actually, when we specify the coordinates, we set them to 0, 0.5, indicating that the center of this link is 0.5 units above its upstream joint. As you'll start to hopefully get comfortable with, as you build up your robot made up of a whole bunch of links and joints, there are things that are upstream that flow up towards the things that you placed in your simulator earlier, and there can be things downstream, things that you place later in the simulation. So we're going to start to use this terminology of upstream, downstream. So far, so good? If I lost anyone? Okay, so this link, we define it as relative coordinates. The next joint that we add, this joint, which is connecting link 1 and 2 together, it has relative coordinates to its upstream joint. This particular joint is sitting 1 unit above its upstream joint. Confused yet? A little bit, okay. All right. And we can continue going, and I would suggest you fill out the rest of this, make a copy of this slide deck or annotate it. It gets a little bit mechanical and mundane, but it's worthwhile just doing it by hand, pen and paper, to get a sense of how absolute and relative joints work. Okay. Partway through assignment 3, I'll give you sort of some instructions about how to know when to use absolute and relative coordinates. The take home here is if a link or a joint has an upstream joint, it's relative coordinates. If a link or a joint, like these two red ones here, this link and this joint, do not have any upstream joint, it's absolute coordinates. Why the heck would a physics engine do this to you? Why not make your life simpler and do everything in absolute coordinates?
When relative is easier to keep track of the different links and joints once they're moving.
Easier to keep track of them once they're moving, possibly. The nice thing about a physics engine is once the simulation starts running and everything starts moving, obviously the positions of these links and joints are changing, but you're not changing them. You're not updating the positions. It's the physics that's updating it. So yes, it would make the accounting and bookkeeping easier if it was for you or for the physics engine. Doesn't really matter from the physics engine's perspective. Other ideas? If you're moving the whole robot or making a copy. So let's assume for a moment I'm going to make a little four-legged robot in my simulation. And here's my little four-legged robot from the side. It's got a main body, 4 upper legs, and 4 lower legs. Let's look at this robot from above. And for now, I'm just going to draw the main body and its 4 upper legs. So we've got 1, 2, 3, 4, 5 links, and 1, 2, 3, 4 joints. I might create such a 4-legged robot, and then in my final project, I might be interested in creating a swarm of robots. So if I go through and figure out the positions of all of these links and joints, plus the joints and links for the lower legs, and then construct the exact same robot but at a different position, I gotta go through and figure out all the absolute coordinates for this second robot. With this combination of absolute and relative coordinates, my job is a little bit easier. If I want to place my second robot in the swarm over here, this is the first link to make up this second robot. I need to use absolute coordinates. So I need to tell the physics engine exactly where I want to place this second robot. But most of the other coordinates for all the parts that make up the second robot, most of those coordinates are relative coordinates. And they're relative to stuff near the center of this robot, stuff that's upstream. So I can leave all of those relative coordinates exactly the same. Makes my life a lot easier. Question?
In this example, would the 4 joints you have drawn for each leg still need absolute coordinates because they won't have joints upstream?
Thank you. Okay, you're anticipating me. So let's have a look at these 4 joints here. Do they require relative or absolute coordinates, given what I just told you over there on the slide? They require absolute coordinates because this joint here, it has no upstream joint. The knee joint that connects this lower leg to this upper leg, this joint does have an upstream joint. So this one would have relative coordinates. This one would have absolute coordinates. So taking that observation, if we go back over here and I'm trying to create my second robot here, I know that I need to manually write down the absolute coordinates for the main body of the second robot. These are absolute coordinates. So do I need to write them down, or do I just leave them the same as in this robot? You need to write them down because they're absolute coordinates. So it's a little bit of a pain. So in my example here of my quadruped, every time I create a new quadruped or add a new quadruped to the swarm, I need to manually come up with and write in 5 coordinates. Why that? Wouldn't it be simpler if there was only one thing in the entire robot that needed absolute coordinates, and then everything else would have relative coordinates? Seems like it would be a little bit easier if the very first link that you create, known as the root link in PyBullet, that I would just write down absolute coordinates for that, and I'd write down relative coordinates for everything else, and then my life would be a lot easier. That I don't know the answer to. That seems easier to me. I have no idea why PyBullet also requires you to write absolute coordinates for joints. If anyone finds out, please let me know. Okay, so it's going to be a bit of a headache in the assignments juggling absolute and relative coordinates. I've given you the rationale for why. The other good news here is that when you get positions wrong and you start up your simulation and the graphics window opens, you usually know it pretty quickly, right? That's why in assignments 3, 4, and 5, and even 6 and 7, when you're adding joints, you're adding sensors, you're adding motors, you're adding neurons, you're adding synapses, the instructions will force you to just add one at a time, start up the simulation, and check that everything is literally where it's supposed to be, and then add the next one. If you're running short on time, trying to get your assignment in on time, and you run ahead and write down all of the coordinates and run your code, and you see a whole collection of joints and links all over the place, kind of hard to debug. So I highly recommend add one thing at a time as you're building up your virtual robot. Okay, any other questions about relative absolute coordinates, joints, assignment 3, going once, going twice? Okay, all right, back to lecture. So last time we finished our introduction to robotics in general and evolutionary robotics. We looked at sort of the intellectual heritage that we all have when we think about building intelligent machines. The history of thought, mostly in the West, over the last few centuries or millennia, depending on how far back you want to go, have sort of carved particular channels that we tend to fall into and think about when we go about trying to build intelligent machines. One of the things I hope that you take away from this course is that there's other channels we can etch in the sand. There's other ways we can approach building intelligent machines, and no one has done it yet. So maybe some of these channels that people tend to follow are the wrong ones. We'll see. Okay. As I mentioned, we've just sort of scratched the surface of some of these ideas, these intellectual underpinnings underneath AI and robotics. Shameless promotion coming up. I teach a course in the fall called Mind Morphology and Machines. It's a graduate seminar, but if you're an undergrad and you're still around in the fall and you're interested, let me know. You might be able to get in. We spend that entire seminar focusing on the philosophical underpinnings of AI and robotics. We just touched the surface in the last 2 weeks. Now we're going to switch mental gears and do the nuts and bolts stuff, the engineering, the science underneath robots. And we're going to look at, in the next 3 lectures, the 3 main tools that underpins robotics and that you're now implementing in your assignments: artificial neural networks, evolutionary algorithms, and physical simulation. So we're going to start today with artificial neural networks. Before we do, how many of you have coded up an artificial neural network before? How many of you are familiar with the backpropagation of error? Maybe half. How many of you could at the board derive the backpropagation of error? I used to be able to do it. I forget how to do it. Okay, so some of you, what you're going to see today is a little bit redundant, and I apologize for that, but we're going to start from scratch. We're going to look at everything that underpins robotics and modern machine learning and deep learning today, starting from the beginning. Actually starting from Bratenberg vehicles. Hopefully, Bratenberg vehicles are intuitive to you now, familiar territory. We've got a robot made up of 2 sensors, 2 motors. We can connect those 2 sensors to those 2 motors either ipsilaterally or contralaterally. And if we then take this little neural network made up of 2 connections at the front, 2 connections at the back, and 2 wires. If we drop that into a robot, we get behavior. Okay. We talked about Cartesian dualism last week. I am going to now sin and throw the body away and keep the brain. So we're throwing the 2 sensors and the 2 motors away. We're keeping the 2 input connections, which in neural network speak are known as the input layer. We have 2 neurons in this very simple neural network that we have now, this naked neural network. And these two input neurons are passive. They're just sitting there waiting for something or someone else out there in the environment to put numbers into them. And today we're going to assume floats. Hopefully we know now that if you put this inside a robot, the thing that supplies values to the input neurons are the sensors. Yeah? Okay. We have in the same way that we have 2 output neurons in the back here that are receiving values, and we'll talk about how these output neurons receive values in a moment. And again, when we drop a neural network into a robot, the values at the output layer, the values that arrive at the output neurons are interpreted by the robot's motors. In the case of a wheeled robot, like the one that you see here, the motor might interpret this number as desired rotational velocity. How fast should the wheel turn? If we just talked about joints, if it's a rotational joint, that number might be interpreted differently by a motor that's sitting at the joint. That motor might interpret this value not as rotational velocity, but desired angle, 90 degrees, 0 degrees, minus 90 degrees. In the case of the robot and the motors, it depends on the motors. The robot can interpret these values as different things. We're going to be just looking at sort of naked neural networks today, so no real interpretation for the moment. We're just going to look at how values flow from the input layer to the output layer. Simplest neural network you can imagine is vehicle 2B, the aggressor. We've got 2 synapses, and these synapses, it's hard to see in this old screenshot that I have here, these little pluses just mean pass the value along. These pluses actually mean, they're meant to represent excitatory synapses. So when we talk about artificial neural networks, ANNs are littered with terminology that's been stolen from neuroscience. So an excitatory synapse, not surprisingly, it excites the neuron that it connects to. The stronger the value at the tail of this synapse, the stronger the value that synapse passes along to the neuron at its head. So we're talking about this particular synapse now. When we're talking about synapses, obviously every synapse has 2 neurons associated with it, one that's sitting at its base and the other one that's sitting at its head. Again, stealing from neuroscience, the neuron that sits at the base of a synapse is known as the presynaptic neuron. And the neuron sitting at the head or the end of the synapse is the postsynaptic neuron. So every synapse has a presynaptic and a postsynaptic neuron. Yeah? So an excitatory synapse simply passes along the value at its presynaptic neuron to its postsynaptic neuron. Nothing too surprising here. Okay, let's add a little bit of complexity. We've added two synapses, we've added two excitatory synapses to our neural network, and we can see in this cartoon example here that the values at the output layer have changed. Why have they changed, or how have they changed? It's adding two values, right? Nothing too surprising here. So if we sit at this neuron, if we want to compute the value at this neuron at any time step, we visit each of this neuron's incoming synapses. This neuron has two incoming synapses, and these two incoming synapses are excitatory. Excitatory synapses simply pass their value along. So we sum up the values supplied by all of the incoming synapses. Not too difficult. Yeah? Okay. High school math here. Middle school math, nothing too complicated. If we were to take this particular if we were to take this particular ANN and drop it back into the body of a Bratenberg vehicle, what does it do?
It goes straight.
Goes straight. What else does it do? Does it go straight at a constant velocity? Does it change velocity? Does it ever stop?
As it gets closer, it increases in speed, it increases in input.
Absolutely. So the closer it gets to the light source, there's more light falling on the two input neurons. It doesn't matter what the distribution of those two incoming values are. Because of the way we're summing things, you can easily convince yourself that these two values arriving at the output neurons and thus passed along to the motors are always the same. The motors at any given time are always commanded to turn at the same speed, which means it always goes straight, but the velocity can change. Faster if it's near a light, but it can't turn towards the light. So we no longer have an aggressor. I don't know what we have anymore, but this is just a reminder that when we make changes to an artificial neural network, that has changes that impacts the behavior of a robot controlled by that artificial neural network. Okay. Let's keep going. Let's add a few more details here. Now we're going to talk about synaptic weights. Up till now, we've just been talking about excitatory synapses. If you've ever taken a neural network course or a tutorial, you'll know that there is a label associated with every synapse in an artificial neural network. And usually these labels are floats that can be either positive or negative. Let's talk about the negative for a moment. What does a negative valued synapse do? Or what does a synapse with a negative weight do? The only thing a synapse ever does is transform values from its presynaptic neuron and supplies it to its postsynaptic neuron. But how? How does it transform it? If you go down into the engine room of ChatGPT or Stable Diffusion, or what was the chatbot that was released yesterday that's making waves?
DeepSeek.
DeepSeek. You go down deep enough, this is what you find at the basic level, these synaptic weights. What does a negative synaptic weight do? Positive values are excitatory. Negative values indicate inhibitory synapses. With a negative weight, or any weight, we take the value of the presynaptic neuron and we multiply it by the weight of the synapse. So the greater the value here, or the more positive the value of the presynaptic neuron, a big positive number multiplied by a negative number gives a big negative number. The more the presynaptic neuron is positive, the more it inhibits or supplies a negative value to its postsynaptic neuron. Everybody see that? Okay, interestingly, in human brains, most of your synapses, and you have 10 to the 14 of them, more or less, most of them are inhibitory. Most of neuroscience is still scratching its head about why. I don't know about you, but from time to time, I think about things I'd really like to do or say to somebody, and sometimes I can hold it back. Sometimes I can inhibit it. One of the tricky things about being intelligent and staying alive in this world is not acting on your impulses. Being able to generate in the motor part of your head exactly what you'd like to do or say, but hold it back. Now, whether there's actually a connection between the prevalence of inhibitory connections in our 10 to the 14 synapses and Homo sapiens sapiens' ability most of the time to inhibit our baser instincts, who knows? That's up to the neuroscientists to figure out, but sort of an interesting coincidence. Okay, that's inhibitory synapses. Positive values for synaptic weights are excitatory. So now that we have these weights, when we want to compute the value of this neuron down here, for example, we, again, like before, we visit all of the incoming synapses, and for each incoming synapse, we multiply its weight by its presynaptic neuron's value. So 0.6 times 0.8, and then there's a second incoming synapse here, so we sum up 0.9 times the weight of this synapse, which is 0.9. So how do we compute the values of all of these neurons? We're computing a weighted sum. We're summing over all the incoming synapses, and those sums are weighted by the weights of the synapses. I'm wasting a lot of time talking about something that hopefully seems really, really simple, to just drive home the fact that this is what's going on in the most basic level of all state-of-the-art deep learning and robotics, at the most basic level. All of those state-of-the-art technologies scale this up to millions or billions, or I don't know if we've reached trillions yet, of neurons and synapses and synaptic weights, but they're all basically doing the same thing underneath. They're doing this. So far, so good? Okay. All right. You'll notice that the value of this particular neuron has gone above 1. And you'll just have to trust me for now. In a lot of applications, we want to try and cap the values of neurons. Some neurons in very large neural networks have a huge number of incoming synapses, and sometimes the sums that arrive in here can be very, very, very positive or very, very, very negative. Going back to our Bratenberg vehicle, we could put a whole bunch of more sensors and wires in here, and the value, depending on what's going on in the robot's environment, the value arriving at the output neuron attached to this motor might be 10,000. And the motor says, whoa, 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 whoa. I can't turn this wheel at 10,000 radians per second. I can't do it. I have a limit. I can only spin this wheel forward at 1 radian per second, or at best, I can reverse this wheel at -1 radians per second. +1 and -1. So often in a neural network, there are real constraints placed on some of these neurons that are coming from outside. Whatever these neural networks are supposed to control or do, something is saying neurons can only have values between certain ranges. In our cartoon example here, the two output neurons in our output layer, they must have values between -1 and +1, but one of them has broken outside of that value. So the last little detail we're going to introduce about basic artificial neural networks are activation functions. These are functions that are applied to the raw weighted sum, and they constrain the activation of the neuron. Activation, another term stolen from neuroscience. Right now, when you're listening to me speaking, if I looked at all of your 10 to the 11 neurons, some of them are firing more quickly than others. They're activated more strongly than other neurons. Okay, so we're going to use sigma here to represent an activation function. There's lots of different activation functions out there. Machine learning researchers get really heated about which ones are the best ones. Everyone has their favorite one. For us, we're not going to worry about that too much. We want to try and cap our output neurons to a value between, let's say, 0 and 1. We could use something like this function, which is the threshold activation function. As long as the x value here is within a certain range, the x value here is this raw weighted sum. As long as that raw weighted sum is within a relatively mild value, we just take that value and set the output neuron to that value. If, however, that raw weighted sum is very positive, far to the right, we're going to cap it at a value of +1. And if that value is very negative, we're going to cap it to -1. Sorry, that should be -1 here, and x less than -1, and a -1 here. Okay. Another favorite one of machine learning researchers is the sigmoid function. Step function, if the raw weighted sum is positive, set the output neuron's value to +1. If the raw weighted sum is negative, set the output neuron's value to -1. That's the step function. Doesn't really matter for our purposes at the moment. As long as we apply an activation function, every time we compute the value of these two output neurons, we can be guaranteed that the values arriving at the output layer here are constrained to the range that we want. So far, so good? Okay. All right, let's have a little bit of fun now. We know how artificial neural networks are built. What are artificial neural networks? There are lots of different things to different people, but mathematically, they're a function. They take a bunch of values at their input layer, and they transform those values into one or more values at the output layer. The most unsexy thing that ANNs are functions. That's it. Okay, some of us are computer scientists in this room, so let's take one of our favorite basic functions. This function has two inputs, two binary inputs, 0 or 1, and this function will spit out one value as a result. What function is it? It's not that early in the morning, is it?
Is it just AND logic?
This is the AND gate, right? This particular function will only output a 1 when input 1 and output 2 is true. Otherwise, it will spit out a 0. That's the function. It's a function that we know and love. Let's embody that function in an artificial neural network. How do we do this? Well, we know that this function requires two inputs, so we create two input neurons that can receive those two inputs. We have one output, so we create one output neuron, and we fully wire up this neural network. Fully wire up means there's a wire or a synapse that goes from every input neuron to every output neuron, which results in a grand total of 2 synapses. Okay, now, in order to finish our artificial neural network now, we need to do 3 things. We've got 3 things that are missing. We do not have a weight for this synapse or a weight for this synapse, and we do not yet have an activation function for this output neuron. Let's start with the activation function. We know that the output is binary. It needs to be 0 or 1. So let's take the step function, and we're going to define a step function that when the raw weighted sum, represented by x here, when that raw weighted sum is above some value, we're going to set the output neuron to 1. And when that raw weighted sum is below or equal to some value, we're going to set the output neuron to 0. So far, so good. We haven't decided what is on the right-hand side of these inequalities yet, but we've now guaranteed that our output neuron can only assume 2 values, 0 and 1, which is good news for embodying our AND function. Okay. I've taken you almost all the way. What are the 2 synaptic weights? And what's the threshold you want to set here? What threshold must the raw weighted sum be above for the output neuron to switch to 1? And if it's below that threshold, the output neuron gets set to 0.
I mean, there are a bunch of different possible answers.
There's an infinite number of possible answers. There's also an infinite number of wrong answers. Give me one right answer.
Weights are both 0.5 if x is above 0.75.
Okay, so we're going to set both weights to 0.5, and then you set the threshold to 0.75. Why 0.75? It's bigger than 0.5, right? So let's run this weighted sum. We put in 0, 0 here. 0 times 0.5 is 0, plus 0 times 0.5 is 0. 0 plus 0 is 0. That raw weighted sum of 0 is below 0.75. Output gets set to 0. 1 out of 4 correct. Let's plug in 0 here, and let's plug in 1 here, and run it again. 0 times 0.5 is 0, plus 1 times 0.5 is 0.5. 0 plus 0.5 is 0.5, which is below your threshold of 0.75. Output gets set to 0. So far, so good. 2 out of 4. I won't do 1 out of 1 and 0. It's the same. Let's plug in 1 here and 1 here. 1 times 0.5 is 0.5. 1 times 0.5 is 0.5. 0.5 plus 0.5 is 1, which is above your threshold of 0.75. And we know that the output value will be set to 1. Well done. 0.5, 0.5, 0.75 will work. Give me one more. Give me another pair of weights and a threshold. Go for it.
0.1, 0.1, and 0.15.
Perfect. Okay, everybody see the pattern? 0.1, 0.1, and 0.05 for the threshold will not work. So we're setting, or we're completing this artificial neural network, and by completing it with different synaptic weights and different thresholds, we embody different functions. All right, so 0.5, 0.5, I chose 0.8. You chose 0.75, close enough. I would encourage you, if you're not familiar with all of this, to play this game a little bit. Set some of your own synaptic weights and thresholds. All right, one more. Or. We can get away with the exact same neural architecture. I'm going to use this term quite a bit in this class as well. Neural architecture is going to be shorthand for how many neurons, how many input neurons, how many output neurons, and how is everything wired up. That's the neural architecture. So that's what's shown in black here. And then you're going to parameterize this neural network to complete it. You're going to give me 3 parameters, the 2 weights and the threshold. What pair of weights and a threshold will embody the OR function? I'm feeling lazy this morning, so let's start with 0.5 and 0.5 again. 0.4. Before, we had 0.5, 0.5, and 0.75 for the AND, and now we have 0.5, 0.5, and 0.4 for the threshold. We've lowered the threshold that the raw weight needs to get over to flip the output neuron to 1. Question?
Yeah, I'm sorry. Could you repeat the original question?
The original question is, what are the 3 parameters that we need to set? What floating point value are you going to choose for the first weight? What floating point value are you going to choose for the second weight? And what floating point value are you going to set for the activation function? That third floating point number is the threshold that the raw weighted sum needs to get over in order for the output to be set to 1. If that raw weighted sum is below whatever threshold you choose, the output neuron will be set to 0. Okay, 0.5, 0.5, and 0.4. I won't belabor the point. I won't go through all 4, but I want you to get in the habit, if you haven't done this before, of mentally sitting down and either doing it with pen and paper or on a stylus or in your head. Plug in 0, 0. Plug in 0, 1. plug in 1, 1, plug in 1, 0, plug in, keep going. And this is simple enough that hopefully you can do these calculations in your head. This value times this value plus this value times this value equals this value. Is it above or below the threshold? Yes, set it to 1. No, it's below the threshold, set it to 0. It's mind-numbingly boring, but when you're doing that, you're doing what all of these devices are doing all the time whenever you run AI. Autocomplete, ChatGPT, Stable Diffusion. That's what's happening underneath. This times this plus this times this plus this times this. Really, really fast. In parallel, usually. Okay, that's the OR function. Bear with me, we're going to do one more. Exclusive OR. As you can see over here, it is still a 2-input, 1-output function. And the XOR function, or anything that embodies the XOR function, must take 2 zeros and spit out a 0, take a 0 and 1, spit out a 1, take a 1 and a 0, spit out a 1, take 1, 1, and spit out a 0. Okay, let's embody exclusive OR in our neural network over here. What pair of weights and what threshold will embody exclusive OR? Yes.
You can do 0.5 and 0.5 again.
Okay.
Your threshold would be between 0 and 1.
Threshold between 0 and 1. The threshold has to be a single floating point number.
Is that also 0.5?
Let's try. 0.5, 0.5, 0.5. Here we go. Let's plug in 0, 0. 0 times 0.5 plus 0 times 0.5 is 0, which is below or equal to 0.5. So we set this to 0. So far, so good. Your solution got 1 out of 4 correct so far. Let's keep going. Let's plug in 0 and 1. 0 times 0.5 plus 1 times 0.5 is 0.5. If the threshold is 0.5, 0.5 is less than or equal to 0.5. So we set the output to 0. Didn't work. So that's not going to work. 0.5, 0.5, and 0.5 will not embody exclusive OR.
You can do one of them 0.5 and the other one -0.5.
0.5, negative 0.5, and what do you want for your threshold?
And then your threshold would be 0.
Okay? Plus 0.5 for the first synaptic weight, an inhibitory connection, an inhibitory weight for the second synapse, and what'd you say, a threshold of 0? Okay? I'm not going to do it. You do it in your head. Does it work? Does this embody exclusive OR? No? Good attempt. What 3 floating point values will embody exclusive OR? There aren't. There is no set of 3 floating point values that will embody exclusive OR. Why are we spending so much time belaboring this point? Back in the 1980s, somebody showed exactly that for a little bit more complicated of an artificial neural network. They wrote a very long paper and said, look, there are certain things or functions that these neural networks will never embody. You can embody exclusive OR, you can do it. You've got some neural hardware running in here. So whatever these things are, they're not neural networks. They're not like what's going on in here. This crazy idea to make these things called artificial neural networks, it's fundamentally flawed. And the US government read this research paper and everybody got very excited and worried, and all the funding shut off for anyone who wrote any grant that had anything to do with these things called artificial neural networks. And AI plunged into its second AI winter. And it stayed in that winter until about the mid-2000s when it slowly started to climb back out again. And here we are in the AI high summer. Okay, lots of drama. Okay, turns out that you can actually get an artificial neural network to embody exclusive OR. What do we have to do? For those that are familiar with artificial neural networks.
We should like add nonlinearity.
We need to add nonlinearity, and we do that in an artificial neural network by going deep. We're going to change the neural architecture. We're going to place two new neurons between the input and output layer. So this neural network architecture, no matter how you parameterize it, will never embody exclusive OR. But if you deepen it by putting some neurons in between and also picking the right parameters, you can get a deeper neural network to do something that a shallower neural network cannot do. Thus the name deep learning. So far, so good? Okay. Now, before we play the parameterization game, which we're going to play in a moment, I want you to notice that we've got our two input neurons as before. We still have one output neuron, because that we know that this function requires two inputs and one output. And we've hidden a couple of neurons inside. We're going to spend a lot of time talking about hidden neurons, hidden layers. Inside you, a vast number of your neurons directly receive photons from your eye, for example, or pressure information from your skin. Those are your sensory neurons. Those are your input neurons. You have a lot of other neurons distributed throughout your body that send an electrical impulse to a small muscle fiber that decreases in length and you twitch. Those are your motor neurons. The remaining vast majority of the neurons in your spinal column and in your brain are hidden. They don't directly receive input, and they don't directly supply output to your muscles. Question?
Is there a correlation between how many transistors you would need to do the same operation and how deep the network has to be?
Yes, absolutely. So if you're going to try and embody this function in digital hardware, you need more bits of that digital hardware to do it. You need more pieces. It doesn't scale one-to-one with neural networks, but yes, you need more stuff to compute more complex functions like this one. Okay, now I've given you a strong hint about how to solve this problem by putting two hidden neurons inside. I, the human, made that choice based on my own personal genius. I know something about the solution to this problem, so we're cheating a little bit already. The goal of AI and robotics is to automate stuff. I don't want to have to decide on the neural architecture. I would like the neural network or at least something else in the AI system to decide for me. We're not going to tackle that today. So I've kind of solved half the problem for you by putting this in. And you'll notice that I have now fully connected the input layer to the output, to the hidden layer. There is a synapse that connects every input neuron to every hidden neuron. So there is full connectivity between the input layer and the hidden layer. And there is also full connectivity between the hidden layer and the output layer. Every hidden neuron has a synapse that connects to every output neuron. There's only one. So I've already made quite a few decisions about how I'm going to embody this exclusive OR function. Why two hidden neurons inside? And if you're new to exclusive OR, that's okay. You might not know the answer to this. There's different ways to embody exclusive OR. What are sort of some general strategies? Have a look at the pattern of outputs in exclusive OR, and let's have a look at the pattern of outputs in OR. Almost the same. Exclusive OR, the pattern of outputs in exclusive OR also shares a lot in common with AND. It can be OR and not OR. That's one way to do it. Yeah. So that what you just said is we can compute or embody exclusive OR if we've already embodied two other functions, OR and not OR. Yeah, I'm not sure that that's true, but there is.
Wouldn't it be or and not and?
Getting closer. Or and not or and not and. I wonder why we just looked at or and. You can compute exclusive OR by combining OR and then negating the and. OR and not, or combined with not and. You can write it out on paper and figure it out. So what we're going to see in exclusive OR is we're going to set these two synaptic weights and the activation function of this neuron so that this neuron embodies OR. And we're going to set the synaptic weights arriving at this neuron, and we're going to set this neuron's activation value so that it embodies AND. Every time we plug in a pair of inputs to the input layer, the values that show up at the two hidden neurons are going to be the result of OR and AND. We'll see how to do that in a moment. Here's OR. Here's AND. Why not AND? We've got one last thing to do. We've computed OR, we've computed AND. We're going to negate AND because... Any ideas?
Were you asking me?
Yes.
Because there's the two inputs that work for exclusive OR are just like a middle two, and the only one that works for AND is the bottom one.
Exactly.
So you take that away from regular OR, then you get exclusive OR.
Exactly. What you just said, we're going to take it away. We're going to compute AND over here, and AND is going to take away the OR. Have a look at the OR. Look at the outputs of the OR. OR shares 3 output values with exclusive OR, and only in the 4th case is it different. So we want AND, which we know fires only in the 4th case. We want, when that AND lights up, we want it to take away or inhibit OR. We want it to suppress OR. Okay, so again, we haven't set any weights yet. Imagine this thing is computing OR and passing its value along to the output. This output is going to receive OR and spit out the OR results in 3 out of the 4 cases. But in the 4th case, this one over here, which is embodying AND, in that 4th case, AND is going to light up. It's the only time it lights up because it's AND. It's only going to light up in this 4th case. And when it lights up, it's going to inhibit the output neuron. It's going to say, You're not allowed to send the 1 that you're getting from OR. I'm inhibiting you, and it's going to push the output value down to 0. Everybody get the general strategy here? Okay, let's stick with this inhibition idea. Let's focus on this synaptic weight. This thing is embodying AND, so this thing is going to light up with a 0 in 3 out of the 4 cases. But on the 4th case, when it lights up as 1, it should push this one down. Tell me about this particular weight. Make it negative, make it an inhibitory synapse. Yeah? This thing is about to do something wrong, and this hidden neuron knows it. And only then does it go in and say, not so fast. Okay. So let's do it. Here's OR over here. So what do we need here, here, and here? The activation threshold. I'm going to use these brackets as shorthand for a single float, which is the threshold. We just did OR. We know that there are 3 parameters that embody OR. Give me 3. 0.5, 0.5, and 0.4 will give us an OR here. So we've got 0.5 here, 0.5 here, and 0.4 here. And you can go through and supply the 4 sets of inputs here and convince yourself that'll give us OR over here. What is this weight, and this activation function?
0.5, 0.5, and
0.5, 0.5, and 0.6 will give us AND. Excellent. So we've got OR over here, AND over here. What do we do with these 3 parameters? We need to set these 3 parameters to just basically copy whatever is coming from OR, and this one has to suppress that copying when it's wrong.
Like 1, -1.
Let's pick 1. That's the simplest thing. Just copy whatever is here into here. 1, and then over here, -1. Remember that this one is and, so in the first 3 cases, this thing is 0, so it doesn't really matter. 0 times -1 is 0. Let's do the 4th case here, the interesting one. We're going to supply 1, 1 up here. This is OR, so we get 1 here. This is and, 1, 1 will give us 1 over here. So we have 1 here, 1 here. 1 times 1 is 1, plus 1 times -1. 1 plus -1, they cancel out, and we get 0. And what was the threshold you gave me here? Something above 0, this thing gets set to 0. We have a deep neural network that can compute a function that a shallow neural network can't do. What this means, what this has meant since the mid-'80s, for those that know, if your neural network isn't doing what you want it to do, make it bigger or make it deeper, and then try and come up with all the parameters that'll give you the function that you want. Okay, all right. All right. This was relatively, hopefully this was easy for you to do for and or. It got a little bit harder for exclusive or. We take one step beyond exclusive or, and you can trust me, it gets really hard really fast to manually devise what all the weights should be. We're now going to ignore activation functions. This holds for activation functions too. But we would like to create some AI that automatically sets these synaptic weights for us. Yep.
So why was the inability to do exclusive OR with only 1 layer regarded as disproving the variableness?
Yeah, it wasn't strictly exclusive or. It was a little bit of a more complicated function that couldn't be done by 3 layers and you needed a bunch more. It was this general realization that they were kind of limited. And it was known that you could, in theory, add more layers and add more neurons and synapses and capture that. But it was too late at that point. Sort of politics took over, and it didn't matter that there was like a theoretical solution to this big glaring problem. Everybody started to focus on the problem. You know, this wasn't going to work. It wouldn't scale up. You'd need too many neurons and synapses to solve problems that we actually care about, which in the 80s was true. It took until the mid-2000s that we could make big enough neural networks and there was enough data to train them that, yeah, we could start to solve problems, or AI could start to solve problems that people actually cared about. People don't really care about exclusive or. Yeah? Okay. All right. So we know that neural networks can actually embody any function as long as we have enough neurons and synapses. That's good. Problem number 1 solved. But then we also need to parameterize it. Find what all these weights should be. That is much, much harder. So around the same time, in the mid-'80s, somebody figured out a way to set all of these weights automatically. For the historians in the room, among historians, there's always this argument about what is the single greatest invention our species has ever made. Hands up if you think it's the wheel. No one for the wheel? How about the stirrup? No? Okay, my vote is for this, the back propagation of air. Okay, there's a mathematical derivation of it. This is not an ANN class, so we're just going to do sort of intuitively how back propagation of air works. Yes?
Is it a convolution?
This is not convolution. So a convolutional neural network is a type of neural network, and you can use the back propagation of error to set the weights or the parameters of a convolutional neural network. You can use the exact same algorithm, the back propagation of error, to set the weights of a non-convolutional network, which is what we're looking at today. Part of why I vote for this as the greatest invention ever. It's kind of general purpose. Not quite, but pretty close. Okay, how does it work? Over here, I've made up a function. This isn't exclusive or anymore. It's something. It still requires binary values for the input neurons and the output neurons. And I have gotten lazy. I haven't even bothered writing in what the outputs should be. But for one of these cases, if you supply 0 here and you take 1 and plug it in here, this function says you should get a 1 at this output neuron, and you should get a 0 at this output neuron. That's what the function is. And now we're trying to set the parameters to embody this function. I'm feeling particularly lazy this morning, so I'm going to just start by setting all the weights to 1. I don't expect that it's going to work. I'm just setting them at random. 1, 1, 1, 1. Simplest thing I can think of. Okay. So we've set all the parameters to 1, which embodies some function. It's very unlikely that it embodies this function. So let's see. We put 1, 1, 1, 1 here. I plug in 0 and 1. You can do the computation yourself. We're hiding the activation function now, so just assume the activation function is the identity function. The activation function does nothing. Whatever raw sum it gets, that's the output. Okay, so if we set them 1, 1, 1, 1, 1, we get at the output layer 1 and 1, but we wanted to get 1, 0. So we now walk across each of the output neurons and compute local error. We got a 1 here, and we wanted to get a 1, so the error is 0. This minus this is 0. No error here. This output neuron is doing what it's supposed to be doing. Okay, let's go to this output neuron. This output neuron is outputting a 1, but it's supposed to be outputting a 0. Did the wrong thing. We're going to punish the neural network. We compute error. 1 minus 0 is 1. We now know that this neuron is behaving and this neuron is misbehaving. So what do? We start to propagate backwards through the network. We're going to now travel from the misbehaving output neuron. We're going to travel upstream. And we're going to look for the culprits. We're going to try and fix the problem upstream so that when we run everything forward again, this error goes away. We're going to propagate the error back, thus the back propagation of error. Okay, off we go. We go backwards. We start here, the misbehaving neuron. This neuron has 2 incoming synapses. So we travel in parallel back along both of them. And I'm going to skip over this part of backpropagation of error. Another beautiful thing about the backpropagation of error is if we use calculus and the chain rule, which we won't do this morning, those tools tell us exactly how to modify these 2 weights so that we reduce error at the postsynaptic neuron. I've cooked this example and made it simple enough that you should be able to do it kind of in your head, right? We got 1 and we wanted to get 0. So how do we change this weight and this weight? Simplest thing is set the weights to 0 and we know we're going to get a 0 here. If we now propagate forward again, we feed in the same 2 inputs and verify this red change. We see that indeed we have reduced the error here. Awesome. Okay, that's backpropagation of error. Last awesome thing I want to tell you about backprop is that it's a localized change. You'll notice that we didn't change all 4 synaptic weights. We didn't have to because this neuron was behaving. We're only identifying local problems or local error, and then we're looking at all of the upstream things that might have caused that error, and we make usually slight changes to them. Here I'm changing a 1 to a 0. That's a big change. Backprop is like going into a huge complicated machine, seeing a problem, working backwards, and then with tweezers making slight changes to maybe not even fix the problem a little bit, but reduce error a little bit. Beautiful algorithm. Okay. All right. Great, but in practice, there's a lot of problems with neural networks and backprop of error. Again, this is not a class, an entire course in ANN, so we're just going to skate over some of these. One of the dirty little secrets about artificial neural networks is we now know that if we make the neural architecture bigger, we can get the neural network to solve problems it couldn't have otherwise. If we make the neural architecture too big, it cheats, or backprop cheats. What do I mean by that? I don't know whether you've had this experience or not, but sometimes you find yourself short on time. You have an exam the next morning. You haven't studied a lot. So you madly try and find the exam from the previous year and the year before, memorize those questions and answers, cross your finger, and hope that the instructor sets the same exam every year, right? You can cheat getting around learning the underlying patterns or mechanisms or tools or ideas that the instructor wants you to learn. Just memorize. Turns out neural networks do exactly the same thing under certain conditions. Here's another truth table over here. It's still a binary function, but you can see it's now a little step closer to a real world problem. We go over to the emergency room right on the other side of the quad here, and we watch patients coming into the ER, and they or their loved one quickly fills out a checklist. Is the patient suffering from symptom 1? Yes or no? Are they suffering from symptom 2? Yes or no? Symptom K? Yes or no? They fill that out, and hopefully in a short period of time, they see a doctor and get diagnosed with whatever problem there is, and I've simplified things by either yes or no. We do this for enough patients passing through the ER, and we start to get a larger and larger Excel spreadsheet here. And we start to notice that maybe there's a pattern here. People that eventually are diagnosed with whatever disease, this output neuron here, they have similar combinations of symptoms coming in to the ER. For most diseases, this gets pretty complicated pretty quickly. Wouldn't it be great if we could learn that function automatically? Let's assume we try to do that with an artificial neural network. We create an input layer with K input neurons that correspond to the K symptoms on the checklist. We have one binary output neuron like we did before, which is going to predict whether or not a patient who fills out the checklist in this way is predicted to have the disease or not. If we're able to train a neural network that does this, maybe this neural network can diagnose folks coming into the ER faster than human doctors can actually see patients. That's the hope, right? Good news for patients and doctors, at least on one level. Okay. Let's assume that whatever this relationship is, it's probably pretty complicated. The human body is a pretty complicated machine. So let's build a very big hidden layer. Let's actually create N hidden neurons inside, where N is some very large number. I don't know how big, so I'm just going to make a really big neural architecture. And then, as patients come in and they're seen by a doctor, I'm going to start to apply backpropagation of error to reduce this error. Wherever this thing predicts patient 1 has the disease, but a doc says, no, 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 patient 1 does not have that disease, non-zero error appears at the output neuron, and we backprop the error, fix the neural network until the neural network agrees with the doc about patient 1. Do the same thing for patient 2, patient 3, keep going. More patients, more backprop, more patients, more backprop. Awesome. Things seem to be working. Or are they? My little cartoon here is meant to represent a cheating neural network. Whatever the weights are in among these synapses, backprop sets them so that this neuron only lights up when the specific combinations of symptoms indicated by patient 1 show up. So this neuron starts to specialize for patient 1. Doesn't know anything about the disease. It says, whenever I see this set of symptoms, I say there is the disease because the patient 1 had the disease. In parallel, hidden neuron 2 memorizes the symptoms of patient 2 and sets this synaptic weight so that it outputs the disease of patient 2. It's memorizing every patient that passes through the ER department. And by memorizing, it gets zero error. Backprop eventually says, there's nothing for me to do. This network is perfect. There's no error. If I'm a lazy instructor and I do set exactly the same exam as I sat last year, and one of you memorizes the exam from last year, you're going to get 100% on this year's exam. What's the problem for you and for this neural network? What happens when patient N+1 enters the ER?
If you don't use this
Absolutely. So patient N+1 enters the ER, they fill out the checklist, and they check off some combination of boxes that none of the previous N patients checked off. This neural network has cheated, it's panicked, and memorized N patients. Now, whatever these sets of weights are, the neural network has to spit something out. So worst case scenario, the ANN says, listen, I've got zero error. I can perfectly predict all these N patients. N equals 1,000, 10,000. I've memorized, I know how to predict all of these N patients. You're giving me the checklist from patient N+1. Trust me, they don't have the disease, send them home. It's a false positive, right? It's a prediction. We don't know from our distal perspective, we don't know that that's what the ANN is doing. We just see the patterns of values that arrive at the output neuron. Hugely problematic. You're a passenger in an autonomous vehicle and something happens on the road that this autonomous vehicle and none of the other autonomous vehicles that belong to the same company has ever seen. Is the autonomous vehicle going to do the right thing or the wrong thing? We don't know. An unsolved problem in AI. It's the Goldilocks problem. If we make a neural network that's too small, it can't solve the problem. If we make the neural network too big, it overfits and is now a seemingly competent but very dangerous machine. How do we know? How do we know what the right size of the neural architecture should be? In my opinion, no one has a good answer to that yet. Okay. Another issue that comes up in artificial neural networks are recurrent connections or recurrent synapses. All the synapses that we've seen so far in these examples, they sort of point downward. They point from the input layer towards the output layer. You can have recurrent connections that connect one output neuron or one motor neuron to another neuron. You can have synapses that point from a hidden neuron back to an input neuron. You can get a whole spaghetti knot of synapses. They don't necessarily all need to flow in the same way. Why would we want to do that? First of all, it messes up the backpropagation of error, the greatest invention of all time. So you better have a good reason for building recurrent synapses into your neural network. One of the nice things about recurrent neural networks is they provide memory. You can go back to the simpler neural networks we just saw, and you'll notice that they don't remember what they did at the previous set of inputs. There's no memory. But once we add recurrent connections, like for example, these two recurrent synapses now, if at some point in time we have two sensor neurons or two input neurons that are receiving these two values, we want to compute the value of this output neuron. This output neuron has 3 incoming synapses. So we multiply this value by this weight, this neuron value by this weight, and this neuron value by this recurrent synapse weight. But what is the value of this output neuron? We haven't computed it yet. At least we haven't computed it at time step t+1. But we did compute this output neuron at the previous time step. So in this case, this motor neuron is combining what it currently senses and its memory. The 1 here is meant to represent its memory of what motor 2 did at the previous time step. Remember our discussion about Turing machines last week? What do Turing machines do and every computer on the planet do? They combine what they're currently sensing with whatever is inside to produce their output. That's what recurrent connections do. We're spending a minute talking about recurrent connections and the fact that they confer memory on neural networks, because for a robot, when it's running around out there in the real world, possibly in close proximity to human beings, it may or may not be useful for the robot to remember what's happened a millisecond before, a second before, a day before, a year before. Actually, it's tricky to know. But this is something you'll explore in the assignments and you can explore in your final project. Okay, I think we're going to stop here with the realization that recurrent connections break backprop, but they have recurrent connections have very good uses for robotics, which is memory. You have a quiz due tonight. Undergrads, you're working on A3. Grads, you're working on 5 and 6. See you back here Thursday morning. Have a good day.